So section 1.7, we're going backwards to chapter 1 to pick up some concepts about graphs and functions that will be helpful for us in the following trig section. So we're going to be talking about graphing techniques, transformations. So the first objective is to graph functions using vertical and horizontal shifts. The next one is going to be to graph functions using compressions and stretches. So those are going to be both vertical and horizontal, compressions and stretches. And then graph functions using reflections about the x or y axes. So if you need some refresher, go back to page 61 to 63 for the library of functions that you should be able to sketch instantly. So they include a constant function, the identity function, the square function, the cube function, square root, cube root, reciprocal, and absolute value. So those should be in your tool bag. If they're not, go to page 61 to 63 and make sure you do have them in your knowledge base. So let's talk about vertical shifts first. If you have the function happening first and then you add some number, so this might look like g of theta equals cosine of theta plus 3. So cosine of theta is the function. We have a function happening and then we're adding something. That's going to shift the graph up k units if the k is a positive number, and it's going to shift the graph down k units if k is a negative number. So notice the order that the adding or subtracting happens after the function has been applied to the x, or we could say the argument. So that makes it more general. So here's some examples. If g of x is x squared plus 2, you take the basic graph of x squared and it goes upward by 2 without changing its shape. So remember, these are called rigid transformations. The graph doesn't change its shape at all, just moves up and down. So here's the absolute value minus 3. So that takes the absolute value graph and moves it downward 3 units. So a different thing happens if you add or subtract a number before you apply the function. So this is the one that I really always have to think about. So this is the one that, how I remember it is, it goes backwards from how it seems like it should. So if you add something to x before you apply the function, it shifts the graph left if the k is positive. So f of x plus 2 shifts 2 units to the left. And if the k is negative, it shifts the graph to the right. So if you have the square root of x plus 2, it's going to shift 2 units left. But if you have x minus 4 quantity cubed for your function, it's going to shift the basic cubed graph 4 units to the right. So it's very important that you notice the order. Here the adding or subtracting happens before the function is applied. So here's some more examples. X plus 2 cubed is going to move the basic cubed graph to the left 2 units. This g of x is going to move the basic square root graph to the right 5 units. And then here's an example of both being combined, and I care about the order because it's going to matter a lot in trigonometry. The first thing that's going to happen is you're going to shift 2 units to the right because that's happening before the function of squaring is happening. And then the second thing that's happening is you're going up 1 unit. So the order matters. You work from the x, what happens to x first, and then outward. Okay, so the second objective is about vertical and horizontal stretches and compresses. So there's actually 4 scenarios here. So if I have the function happening first and then the multiplication, and a is between 0 and 1, the graph of f is compressed vertically to make the graph of g. So if the graph used to look like this, and a is between 0 and 1, it's going to make the mountains less tall and the valleys not as low. So hills are less tall, valleys less deep, zeros don't move. So this is really important. Anything that was a 0 still is a 0. If a is bigger than 1, the graph of f is stretched vertically. So you need two words to describe this transformation, whether it's compressed or stretched, and horizontal or vertical. So again, the hills are taller and the valleys are deeper, but the zeros don't move. So notice the order. The multiplication's happening after the function has been applied. So if I have x squared and then I multiply it by a half, the graph is going to be compressed vertically. It's going to be half as tall. And then if I multiply by 3 after I do the square root of x, this is going to stretch the graph vertically and make it taller. So then we have horizontal stretching and compressing. And again, this is somewhat counterintuitive. If a is between 0 and 1, and you multiply by a before you apply the function, this seems very counterintuitive, but the graph of f is stretched horizontally to make the graph of g. So the peaks and valleys don't change their height or depth, but the zeros spread away from each other. So if your curve looked like this, the height of the hills and valleys doesn't change, but the zeros spread apart from each other. If the a is bigger than 1, the graph of f is compressed horizontally to make the graph of g. So again, the peaks and valleys don't change height or depth, but the zeros move closer together. So again, notice the order. The multiplication happens before the function's been applied to the x. So if we do the cosine of 1/2 x, it's going to stretch the graph and make it twice as wide. But then if we do the sine of 3x, the graph is going to be compressed. Whatever it was doing in this much space, now it's going to do that same behavior in 1/3 as much space. So the last thing we're going to talk about is reflections. And if the negative comes after the function, that causes the graph to reflect about the x-axis, to create the graph of g. But if I do negative of the x and then do f, that's going to cause the graph to reflect about the y-axis to create the graph of g. So notice the order. If I have g of x equals negative square root of x, that takes every value of square root of x and changes it to a negative number. So it reflects it across the x-axis. But then if I do h of x equals the square root of negative x, now I need to be putting negative numbers into the function so it reflects the graph about the y-axis. Okay, so here's some practice exercises with combinations, and we're going to do some graphing using these techniques of transformation of graphs. And then we have some more exercises here where we're going to look at this f graph that's illustrated here and figure out what all the values are of these transformations. And then we're going to talk a little bit about asymptotes. So we have horizontal asymptotes. Says if the value of your function approaches some number as x goes to infinity or negative infinity, then y equals L is a horizontal asymptote. So do note that the graph of a function may cross a horizontal asymptote. We can have horizontal asymptotes, and we can have graphs that cross them. Vertical asymptotes, on the other hand, a graph may not intersect a vertical asymptote. And as x is approaching some value c, if the value of the function is going to infinity or negative infinity, then x equals c is a vertical asymptote. It's the equation of a line, so you need to label it. So this would be the vertical asymptote x equals 1. So that will help us when we go to do trigonometric graphs, and that's all we have for section 1.7.